In the previous chapters of the course, we've seen mainly how we classify gap topological phases. In this chapter, we will see gapless topological phases, what are their properties and unique features. What we will see is that the gapless topological phases can be thought of as an intermediate phase between trivial insulators and topological insulators. So let's consider a trivial insulator. We have its conduction and valence band dispersion in the Hamiltonian, which looks something like this. And now we can tune the relative position in energy by some perturbation, for example, spin-orbit coupling. When we do this, one result that may happen is that the conduction and valence band will interpenetrate, giving rise to this line of degeneracies, which we call a nodal line. Along this line, we have Dirac dispersions in 2 dimensions and free dispersion along the nodal line. One thing that may end up happening is that we'll have some mixing term, the off-diagonal terms, that will hybridize the conduction and valence band together, giving up to a gap and a trivial insulator. However, we may have situations where symmetries prevent these bands from hybridizing. For example, if we have mirror symmetry and the valence and conduction band have different mirror Chern numbers, they cannot hybridize. Therefore, a gap is not induced, and the nodal line of degeneracies is protected by the mirror symmetry. Another option is when we consider spinless electrons, or at least electrons that exhibit vanishingly small spin-orbit coupling. We retain time reversal symmetry and inversion symmetry. In these cases, the off-diagonal terms are identically equal to 0, and therefore we don't get hybridization, and again, we end up with a nodal line semi-metal. One interesting thing that can happen, and we will consider next, is what happens when we do consider spin-orbit coupling and break either time reversal or inversion symmetry. In these cases, we will generate distinct topological phases, gapless, out of this nodal line semi-metal that we've seen so far. So let's go back to the previous Hamiltonian and retain the off-diagonal terms. This is how the general solution of this Hamiltonian looks like. Again, we have the conduction and valence electron as well as the hybridization term. What can happen now when we introduce spin-orbit coupling is that the gap will be induced along the nodal line, but at a finite set of points. For this to happen, we need the hybridization term to be equal to 0 at certain point in the momentum space. For this, we need both the first term and the second term to be non-zero. Equating the first term to 0 gives us a 2-dimensional plane in the 3-dimensional Brillouin zone along which it is nulled. For the second term, we need both the real and the imaginary part to be equal to 0. Therefore, we get 2 more constraints, and in general, we have 3 planes, 2-dimensional planes, that constrain our equation. In some cases, these 3 planes will intersect at a single point, which will be the nodal point. This does not have to happen, and for sure it does not happen in 2 dimensions because we have 3 constraints, or in 2 dimensions, this equation is over-constrained. However, in 3 dimensions, we may very well end up with some distribution of nodes in the 3-dimensional Brillouin zone. So now we have this distribution of nodes, and each one of them serves either as a source or a drain of Berry flux, meaning that Berry curvature is either emanating from or flowing towards these nodes. So now we can think of a 2-dimensional fictitious plane that cuts through the 3-dimensional Brillouin zone. Whenever it is positioned outside the volume that encapsulates all the nodes, 0 Berry flux will thread it. However, now we can tune this 2-dimensional plane across the Brillouin zone. What we'll find are positions where a finite Berry flux is threading this two-dimensional plane. In that sense, this two-dimensional electron gas behaves exactly as a quantum Hall state. This means that some boundary mode has to be induced. What happens in topological semimetals is that we get these open contour bands, the Fermi arcs, which are characteristic to a nodal topological semimetal. The total Chern number has to be still 0. Here we're looking only at a single Brillouin zone. However, due to the periodicity of the crystal, this Brillouin zone is replicated infinite times. Having non-zero Chern number will end up with a diverging Chern number in the unfolded scheme. Even though the total Chern number equal to 0, each band may carry a non-zero Chern number. So we now have some distribution of nodes in the three-dimensional Brillouin zone. Let's see what additional constraints are induced by time reversal and inversion symmetry. Inversion symmetry requires that the chirality of pairs of nodal points on either side of the origin, the gamma point, will appear antisymmetrically. On the other hand, time reversal symmetry requires that they appear symmetrically. Therefore, in the presence of both inversion symmetry and time reversal symmetry, we can either have a doubly degenerate Dirac semimetal or an insulator. If we break either inversion symmetry or time reversal symmetry, we lift the degeneracy of the Dirac semimetal and may end up with a Weyl semimetal. Now we have a Weyl semimetal. Let's see what adding additional perturbations to the Hamiltonian may do to the respective Weyl nodes in the bulk. One thing that may happen is that the Weyl nodes will come closer to each other until they annihilate, a gap will open, so we have a bulk gap. However, on the surface, there are no boundary modes left. This is indeed a trivial insulator. Now let's generate the Weyl semimetal back from our trivial insulator and shift the Y nodes in the Brillouin zone such that they approach their counter pairs. By doing so, again, a gap will be induced in the bulk. However, now we're left with some sort of topological boundary modes. These are indeed the topological Dirac surface states of a topological insulator. So by this, we've seen how annihilating, pairing pairs of Weyl nodes may give rise either to a trivial insulator or to a topological insulator. So what we've seen is that by tuning a system parameter, we can go from a normal insulator through a Weyl semimetal till we end up in a topological insulator. This tuning parameter can be, for example, spin orbit coupling, and in between we have the topological semimetal phase. To get a Weyl semimetal, we must break either inversion or time reversal symmetry. When both are retained, we're left with a Dirac semimetal. By this, we've seen how the topological semimetals are indeed an intermediate state between the normal insulator and the topological insulator.